Okay, it's time to start. So let's go on in this overview of internet, and we are already at the network layer, which is the layer we have to focus and explain into details. And we were talking about the virtual circuit service, which is one of the possible services offered by the network layer. And we have seen the phases needed to set up a virtual circuit, that is the opening phase, and then transferring of data, and the release of the circuit. We are always talking about packet switching, so even if there is this setup, still packets are treated as individual entities by all the intermediate nodes. And when there is the setup of a virtual circuit, we have to first make a call initiation request that comes from higher layers to the network layer. This request is in the form of the so-called protocol primitive. It is an instruction or a command that is recognized by a given protocol. And we are talking about primitives when we are referring to messages that are sent from a protocol layer to another protocol layer inside the same site. So in this case, the initiate call command is issued by the transport layer to the network layer in the sender or the source host. Okay. So call initiation is the instruction that starts the setup phase, and you see the red long arrow in the bottom represents the first sending of control messages from the source to the destination in order to initiate the call. When the network layer of the destination receives these messages, then it notifies the layers above, the transport layer, that there is an incoming call by another primitive that is, in this case, transferring of messages inside the destination host. So when the network layer has notified the incoming call, then the transport layer sends a command of accepting the call, and there is the second arrow that you see coming back, the red arrow across the network. This represents the sending of the confirmation messages. So when the confirmation message gets back to the source, then the setup is confirmed, so the call is connected. And at this point, the network layer notifies the transport layer that there is the virtual circuit setup, and so data flow can start. It's the blue arrow that you see there, and data can be received at the destination. So you see that a complex service like the virtual circuit service requires a lot of different communications between the network layer and the upper layers, so a lot of primitives. This is the signaling phase represented in a sample network with the signaling packets that are sent through the network. They follow a certain path, and once this path arrives to the destination and is confirmed back, then the data transfer phase will use the same path, exactly the same path, to transfer all the data packets. So this is basically virtual circuit service, which is a general concept. There are several protocols providing this kind of service, as we have seen, ATM, MPLS, and so on. We will also see in the next chapter the flow-based switching, which is typical of SDN architectures and OpenFlow in particular. Flow-based switching is not exactly virtual service. It's a way to manage the network layer, so it's related to the network layer as well. In this case, we have a certain. We could think about it as a form of virtual circuit because there is a phase of let's say programming of the single intermediate nodes before start sending data, or let's say when the first packet of a flow flows through the network. And once these intermediate nodes are configured so that the flow can be recognized by the intermediate nodes, then forwarding of packets through the intermediate nodes is very immediate. It's not based on a simple lookup in a table, but is based on the packet classification process that we will see later on. So it can be regarded in some way as a form of virtual circuit switching. The classical virtual circuit switching, not the flow-based switching, but the virtual circuit switching, works in this way as it is shown here in the picture. Here you have the network on the left, top left. The nodes are marked with A, B, C, D, E, and F, and hosts are attached to the nodes. In this simple case, you have one host per node, and the host is represented by the symbol H with the letter of the node it is attached to. So on the left you have a table of virtual circuits, and each virtual circuit has to be set up before setting up. So in the setup phase, the path is decided, so the path through the network. So for example, the first virtual circuit you find in the table is this one, from the host attached to A, the host attached to D, and the path is A, B, E, and D. In order to set up this circuit, so this is the path represented. In order to set up this circuit, we have to write an entries and write a new entry in each of the tables, the forwarding tables that are located in the nodes that are crossed by the virtual circuit. And so here you have the tables below the nodes, and you see that each table has two columns, one for the input and one for the output. And in each column there are two subcolumns. One is for the interface, and in case of the input interface is in case of the input column is the interface where the packet is coming. So from which the packet is coming, so the input interface of the packet. And then the second subcolumn is the virtual circuit identifier. In the output you have the interface where to send the packet, and in the second subcolumn a new virtual circuit identifier. In fact, the virtual circuit identifier is not an ubiquitous label. Is only valid link by link, and when you define a virtual circuit, you have a set of virtual circuit identifiers, one per each link that is crossed by the virtual circuit. And all the intermediate nodes not only perform the switching operation, so forwarding the packet to the correct output interface, but they also perform the so-called virtual circuit swapping, virtual circuit identifier swapping, or label swapping. It means that once a packet is identified by the virtual circuit that is written in the header when the packet is coming to the node, then it is routed on the proper output interface, and the node, before retransmitting the packet, rewrites the field in the header that contains the virtual circuit, writing a new value of the virtual circuit. The new value of the virtual circuit will be recognized by the next node, okay, that will do the same operation. So, for example, here you see that this virtual circuit starts at node A, where the node receives packets from the interface that is connecting with its local host, page A. And packets that are coming in has virtual circuit identifier 41. So by the pair input interface and the virtual circuit identifier, A is able to identify a specific item in the table, so a specific row in the table. And so in the table, A reads the output column, which contains B, that is in the interface where to send the packet, and 23 is the new value of the virtual circuit identifier to replace in the header. So the packet will leave node A going towards node B with the new virtual circuit identifier 23. Then in node B you have another entry where you find A, that is an input interface towards A, the identifier 23, then the corresponding output column says send the packet to E, to node E, so the interface towards node E, and replace the virtual circuit identifier with the new value 6. And so on until the packet reaches the destination. And this is done for all the packets of the flow. Okay, so once the flow is set up and remains active, all the packets that are sent from the host HA with a virtual circuit identifier 41 will arrive to the host HD, okay, following the same path. This is another example where you have this virtual circuit number 7 in the column. That is the path and the corresponding entries in the virtual table. So when you have the virtual tables, the forwarding tables of all the nodes, by looking at the forwarding tables, it is also possible to find out what is the list of the virtual circuits that are active and their path. So this is the virtual circuit service. On the other hand, we have the datagram service. In this case, the information units, the packets that are named datagrams, are treated as individual entities. So the datagram service is always connectionless. There is no need to set up any kind of flow or connection in advance. And packets are forwarded on the basis of a destination address. The destination address is written in the datagram header. Each node has a table similar to what we have in the previous case, but in this case the destination address is an ubiquitous and unique identifier. So it is not changed link by link, but each possible destination in the network is associated or has a corresponding unique destination address. The routers, since there is no setup phase, they don't keep any state information about the connections. So there is no concept as a connection setup and connection teardown. And so the packets may arrive at the intermediate node at any time, and they are always routed according to the destination. For consequences, for example, that if a node receives two packets from two different input interfaces, but both with the same destination address, they will be forwarded to the same output interface. So there is no distinction based on the input interface. And in terms of service primitives, so the commands that are exchanged between the network layer and the upper layer, we have a very large simplification compared to the previous case, because here we have only the instruction of sending a packet and receive a packet. So this is an example again with the network that is the same as I shown before. This is a routing table of node number B, which is an intermediate node on the top. The routing tables have two columns. One is a list of the destinations, and the next column is the second column is the next hop, where to send the packet in order to deliver it to the next intermediate node, or if this is the last node, to the destination host. These routing tables may change in time. So, for example, when you send the first packet through B, packet number 1, the state of the table can be the one that is depicted here. So the destination of the packet is D. So B is sending the packet to the next node, next hops C, according to the table. Then the table may change, and other packets that are flowing through the same intermediate node go into the same destination. For example, in this case, destination D again. They may be routed on a different output interface. In this case, the interface is F. Okay, so they are routed towards F. And so, since there is no concept of active connection, packets that are going to the same destination may follow different paths, not a single path, as in the virtual circuit case. And so the datagram service is much simpler than the virtual circuit. Obviously, this implies that there are some drawbacks, as always in engineering. When you pay more, you have more advantages. So the drawbacks are the following. First of all, since packets may follow different paths, you may have out of sequences. So in this example, that is similar to the previous slide, you have the first packet that is going through B, and it will reach the destination in following a path that is 3 hop long. So it's A, B, C, and D. Then the routing table of B changes, and the packet number 2 is sent towards F. So it will follow a path that is A, B, F, E, and D. And so it is 4 hops long. Okay. Then the routing table of B changes again. Packet number 3 will follow the path A, B, E, D, that is again 3 hops long. The result is that B receives packet 1, then packet 3, and then packet 2. Because if you assume that the number of hops is proportional to the propagation delay, packet number 2 arrives later than packet number 3, but packet number 2 has been transmitted before packet number 3. So at the end, D receives the packets out of order, so in an out of sequence way. If the network layer is offering the datagram service, the network layer is not able to face itself this situation of out of sequence. There must be something above that, in case of internet, is the transport layer, in case of the TCP protocol, that will reorder the packets. Then you may have packet loss. For example, here packet 1 arrives to the destination, packet 2 is sent from node B to node F, and then it is received correctly in node F, but then node F goes out of service. Okay? So the packet is lost. Packet number 3 will follow another path in order to avoid the node that is in failure conditions. And so the node D at the end will receive only packet 1 and packet 3. Okay. Again, also in this case, if the network layer is offering the datagram service, the network layer itself is not able to recognize that there is a loss of packet. Okay. So the packet is lost for the network layer. Duplication, another possible undesirable situation. Packet 1 arrives correctly, packet 2 and 3 are sent towards node F. Then node F has the routing table that is indicating E as the next hop, so it starts sending packet 2. Packet 2 is transmitted correctly to the node E, but as soon as the packet is received by node E, this link goes out of failure. And so packet F assumes that the packet that is transmitted has not been received correctly by the next hop. Okay. This is, for example, if there is a mechanism of confirmation at the data link layer, so below the network layer, maybe that packet F sends the packet but does not receive any acknowledgement that the packet has been received correctly. So the packet has been received correctly, so packet, the node E forwards it to the destination. But since packet F, node F believes that packet 2 has not been received, it retransmits it using another path, so it translating it directly to D. So at the end, D receives 1, 2, 1, 3, and two copies of packet 2. Okay. And also in this case, the network layer is not able to recognize that the two packets, number 2, the two copies, are two copies of the identical packet. There is must be something above that provides for these situations. So going back for a minute to the complete protocol stack we have already introduced. For this course, it's relevant to understand very well what are the protocols that must be implemented in the router. As we have said, the transport layer and the application layer, that is not presented here, are all implemented in the host, so they are not present in the router. In the router, you find the IP protocol and then the implementation of the lower layers, data link layer and physical layer, because of course the router has physical interfaces in order to communicate with the rest of the network. The IP protocol needs some control plane infrastructure implemented inside the router, so control plane intelligence, in order to perform the routing and the forwarding operation on the IP packets. So we need a routing table. The routing table tells the router what decision to take in order to forward the packet that is going to a certain destination, sending it to the correct output. And this is basically the function that is the basic function of the IP protocol. The IP protocol is the protocol implemented in the router at the network layer that is acting on the data plane, because it is needed to handling data information, data packets. It's very important that this routing table that is read during the data plane functions is written in some way. So who writes the entries in the routing table? The entries in the routing table are written by the control plane. Okay? And the control plane in Internet is based on a set of routing protocols that are distributed, RIPO, SPF, and BGP. Distributed means that they require exchange of information between routers. So the routers, when they are acting on data plane, they cannot be source or destination of traffic, because they are just intermediate nodes. but they have also to manage control plane protocols, and in this case they are becoming source and destination of traffic, because the messages of these routing protocols are exchanged between the routers in order to agree on the routing plan of the network. And then there is also a protocol or set of protocols, but the most common one is ICMP, that are used for the management plane. So they are used for configuration, error reporting, and signaling of exceptions. So in each network there is always a data plane, a control plane, and the operation and management plane. Okay, questions? So if there are no questions, I can go on. Here you have a set of extra slides that you may read through. I leave for the second part of this overview that is dedicated to internet looks more closely to the basic functions that are performed inside the network layer. And here we need to understand or review what happens to an IP packet when it is received by a router and it is forwarded towards the destination. So we will look at the routing and forwarding process, but in order to understand the routing and forwarding process in the framework of the more general framework of the overall network, it's also important to review the addressing system. So how IP addresses are assigned in internet. So maybe these concepts are already familiar to you, because they are the usual concepts that are provided by basic networking courses, but maybe you had these courses long ago, so you forgot, or you didn't have these courses. So it's important before going on to understand this general framework. So the IP addressing system is based on a numeric address that in the case of IP version 4 is of 32 bits. Okay, IP version 4 is the oldest implementation of the IP protocol. It is still by far the most popular implementation, so you find almost everywhere IP version 4, except in some networks. Some networks supports IP version 6, which is the newer implementation. Actually not new, because it has been standardized also IP version 6 many years ago. In IP version 6, addresses have been expanded, so they are not 32-bit long, but they are 128-bit long. So they've been expanded because in IP version 4, the address space with the expansion of internet and the increasing number of hosts got rapidly exhausted. So we don't have IPv4 addresses free anymore to assign to new hosts today. We have to reuse the old ones in some ways. I remind you that these addresses are used in a datagram service, because IP is providing only the datagram service, not the virtual circuit. So they must be unique identifiers. So each host or interface identified by an IP address is identified by a unique address, so to be ubiquitously reachable. Okay? And therefore, you cannot assign the same address to two different interfaces all over the network. We'll see that there are some exceptions to this rule for the so-called private addresses, but that I will talk about it later on. So as the general rule, you cannot assign twice the same address in an overall internet. Since you have these 32 bits, it means 4 octets or 4 bytes. The most common way to represent these addresses is by the dot decimal notation. That is, you use 4 decimal numbers, each one for each of the bytes, separated by a dot. And the first bits on the left are the most significant bits, and the last on the right are the least significant bits. And the same for the bytes. IP addresses are split into two parts. One is dedicated to the identification of the network, and the second part is dedicated to the identification of a specific host inside the network. Okay? The part dedicated to the network is always the one that is starting with the most significant bit or the most significant byte. The part that is identifying the host is the one that is ending with the least significant bit. The network parts so corresponds to the first n bits of the network, and it is called address prefix. The separation between the address prefix and the host identifier is variable. So the length of the part dedicated to the identification of the network in terms of number of bits changes from network to network. For example, here you have a prefix that is a network prefix in binary forms, that is 1, 0, 0, 0, etc., 1, 0, and so on. And then you have a star. This means that the network prefix is 2 byte long, so 16 bits long. The rest of the 32 bits are dedicated to the host, and this network that is identified by that identifier with 16 bits represents all the possible addresses that are 2 to the 16 that begin with the bit pattern that is represented there. Okay. So the network prefix is also the common part that is shared by all the addresses of host that belongs to the same network, Another example, 130.86/16 is another way of indicating a network prefix. Indicates that the length of the prefix is again 16 bits, and the binary values of that 2 bytes, that first 2 bytes, is it is shared by all the addresses that belongs to the same network. The star also is another way to indicate the same concept. The star stands for any possible number. There is another alternative notation that is equivalent to the previous ones. We can provide the network prefix in terms of a 32-bit address and another 32-bit number that is called the net mask. The net mask is always composed by initially a set of bits with logical value set to 1, and then at a certain point the one logical values 1 stops, and you start with the logical value zeros. Okay, so the net mask is always, if you see it in a binary form, a set of ones followed by a set of zeros, and composed by a total 32 bits. So you have the ones in correspondence to the bits that are dedicated in the associate address to the network prefix, and the zeros are in the positions that are dedicated to the host identifier. So the network mask is an alternative notation, but it is also important because it can be used by machines, okay, to separate the network part from the host part when you have a certain IP address as an input. And in particular, if you receive any 32-bit address and there is a net mask that is specified by an AND operation, the result of the AND operation is the network prefix that is contained inside the address when it is written, when it is read by that net mask. Okay. Is it clear up to now? So, to summarize, we can identify the network prefix by the notation that is slash and then the number of bits that are dedicated to the network prefix, or the length of the network prefix. Or we can write the network prefix by the decimal values of the bits of the bytes of the network prefix followed by stars, or the equivalent binary version, or by using the net mask. So we talked about network address or network prefix, but we did not yet specify what we mean by network. So what is an IP network or IPNet, which is an entity identified by a specific network prefix? Actually, the IPNet is let's say logical concept, and you can define it as the set of the pool of hosts or of network interfaces which are addressed with an address that belongs to the block identified by the network prefix. So when you have a network prefix, as we have already said, actually you are considering not a single address but a block of addresses. All network interfaces which have an address belonging to that block belongs to the same IP network, belongs to the IP net identified by that specific network prefix. So, for example, if you see the picture above and we only refer to the logical meaning of IPNet, IPNet identified by the network prefix 193.17.13.0, which is 24-bit long, so it's a network prefix of length 24, represents the block of addresses that goes from 193.17.32.0 to 193.17.32.255. Okay? So this block of addresses is the network, and all the interfaces which are configured with an address belonging to this block belongs to the specific IPNet. This is a logical concept. In most of the cases, on the so-called good practice cases, this logical concept is backed by or corresponds to a physical concept, because the IPNet is usually corresponding to a local network to which all the that is interconnecting all the interfaces with an address that belongs to that specific block. So in this case, that is represented here, you see that, for example, IP address .55 is assigned to the host B. The IP address .45 is assigned to the host A, and the IP address .254 is assigned to the interface of a router that is C. B, A, and C are all connected to the same local network. In this case, we can assume that the local network is, for example, Ethernet, and in fact, you can see that these A and C all have a corresponding MAC address. Okay? The MAC address is an address that is recognized at data link layer, so by the technology that is used for the local network. And since all these interfaces are connected by a physical local network, they are able to exchange data each other, so they are able to communicate. So an IPNet usually is associated to a local network where a pool of interfaces are able to communicate on the data link layer, and these interfaces are assigned an IP address that belongs to the block referred by the net identifier. In an IPNet, you have hosts, so interfaces, so network interfaces of the hosts, and usually at least one router. Because if you don't have at least one router in the network, this network is isolated from the rest of the internet. So in order to connect the network to the rest of the internet, you need a router which is connected to this network. Routers are not, you cannot say that a router belongs to an IPNet, because by definition, the router must have at least two or more, usually more, network interfaces. So one interface of a router is connected to a specific IPNet. The other interfaces must be connected to other IPNets. Otherwise, you don't have communication. And therefore, you can say that a host has a specific IP address, but you cannot say that a router has a specific IP address, because the router has many interfaces, and you identify with an IP address each interface of the router. Okay. Also, hosts can have multiple interfaces. For example, in your PC, you always have the wired transceiver, so the connection to wired internet, and the Wi-Fi interface. They are two different interfaces. In fact, they have two different IP addresses, and they are also two different MAC addresses and so on. However, in the typical case, only one is active at the time. So when you are using Wi-Fi, you are not using the fixed internet, and vice versa. So in a standard PC, you are not able to communicate from one interface to another. Okay? So you can say that the PC is associated to a specific IP address, has a specific IP address. This is not true for the routers. The routers have many interfaces with many IP addresses active at the same time. So IP is an internetworking technique. Thus, when you are forwarding the packets, they must be transmitted from the source host to the first router, then to the first router to the second router, and so on until you receive the last router, which then will send the packet to the destination host. So we can distinguish two different forwarding situations. The direct forwarding is when the destination is in the same network, in the same IP net, usually the same LAN, of the source. So you are sending a packet from a source to a destination, and they are connected directly by the same network, and they can speak, for example, on the layer 2, on data link layer. Indirect forwarding is when the destination is not in the same IP net as the source. So in this case, you have always to cross at least one router, and so you have to make at least 2 hops to reach the destination. Let's look at direct forwarding before. How this happens. This is quite an important concept that you must know. Who knows? Who remembers these things? 1, 2. Okay, so it's important to take note about it, because this is the basic, not only the basis, not only of a part that will follow about IP address lookup, but also when you will do the project in SDN. So what happens when you are doing the direct forwarding? Assume that you have host B that has to send a packet to host A, and the packet is an IP packet, so it's sent at layer 3. We are in the situation where B and A are connected on the same physical network, so they have 2 IP addresses that belongs to the same IP net. The IP net is again 193.17.31.0, and the 2 addresses, as you can see, belongs to the same IP net. They have also MAC addresses because they are connected to the same layer 2 network. So when the entity that is implementing the IP layer in B receives from the layer above the instruction, the command to send the packet to A, with this command along with the service primitive, the upper layers also tells the IP layer what is the destination address to use, okay, because it is an information that must come from above. So the IP entity of B knows the IP address of A, okay. The IP entity of B also knows the IP address of the interface that is connecting B to the network, so the local interface. So the first operation that is carried out by the IP layer in B is to compare the destination address with the address of its local interface. Okay? And by this comparison, B is able to discover that A belongs to the same IP net as B. So they are connected on the same network. So this tells B that the forwarding must be done in the direct mode. How to reach A? Once we have decided to send the packet in the direct mode. At this time, the IP implementation in B have to instruct the data link implementation, so layer 2 implementation in B, that what it will be sent in terms of packet must be encapsulated in a frame, so in a protocol data unit of the level 2 of layer data link, and this frame has to be transmitted to A. In order to send the frame to A, the data link implementation in B must know the MAC address of A. Okay, so another function of the IP layer is to tell the layer down, the bottom layer, the layer below, which is data link. What is the address, the MAC address to use, or layer 2 address to use to send the frame? And the frame must be sent to A. Where to retrieve this information? Inside B there is another table which is called the MAC table, or the ARP table. This table contains two columns. In one column there are a set of IP addresses, and in the other column you find the corresponding MAC addresses of each IP address. So for instance, in the IP address corresponding the IP address in the entries related to the IP address of A, there is the MAC address of A. Once this table is available, then the IP layer in B can instruct the data link layer to B on where to send the frame. Okay. This table is again must be written by somebody, so it's available and is read by the operation of the IP layer, but it must be written by somebody, and it is written by another protocol that is distributed that is called ARP. Okay, it is a protocol that is dedicated to learn the MAC addresses of the IP addresses of hosts connected in the same network. So then the packet can be forwarded. The packet is not transmitted directly, but it is encapsulated in a frame, a layer 2 frame, where you find the IP packet in the payload, and there is a layer 2 header. The layer 2 header contains the destination MAC address of A that comes from the table, the ARP table. It contains also the MAC address of B, incidentally. Inside the payload you find the packet. In the packet you have the IP header, which contains the destination IP address of A and also the source IP address, which is the address of B. Okay. So this is direct forwarding when you are sending a packet from one source to a destination belonging to the same network. What happens in the other case, in direct forwarding? So here B must send a packet to the IP destination that you see there, 131.17.23.4. Okay. The destination IP address it comes from the upper layers. So when the upper layers request the IP layer to send this IP packet, they also tells the IP layer what is the destination IP address to use. First operation of the IP layer in B, compare this IP address, the destination IP address, to the address of its interface, okay, the interface in the network. So by this comparison, B can immediately realize that this IP address does not belong to the same IP network. So B cannot send the packet with the direct mode, but you must use indirect forwarding. This means that the packet must be sent to the router, okay? And the router is the first hop to be reached in order to get out of this network. Usually there is always a router that is configured in each network that is called the default router or default gateway. And in fact, if you have ever seen the configuration panel of your interface, network interface of your PC, you have always to specify a default gateway, that is the router to reach when you want to go outside the network. So what happens in this case? The packet must be sent to the interface of the router that is connected to this network. So it must go to the interface with the IP address 193.17.31.254. This is not the destination IP address, it's only the IP address of the interface of the first router. In any case, the first hop, so the packet that is originated in B must be transferred to the interface of C, and this is possible only exploiting the capability of the layer 2 network that is interconnecting B with C. So B needs to retrieve the MAC address of the C interface, the interface of C, and therefore it will use again the same ARP table, this time looking for the entry corresponding to the IP address of the interface of C, which is the gateway interface. And again, if we go back to the configuration of your network interface of your PC, you have to specify as default gateway an IP address, and this is the IP address of the interface exactly of the default gateway, the key that is used to look into the ARP table in case of indirect forwarding. So the packet is transmitted to C, and it is transmitted using a layer 2 frame. In the layer 2 frame you have the IP packet in the payload and the layer 2 header. In the layer 2 header you find the source, the MAC address of B as source address, and as a destination MAC address there is the destination, the MAC address of the interface of C. What is what you find inside the packet? Again, you find the IP packet. Source address is the IP address of B. Destination address is not the address of the interface of C, but the destination, the address of the final destination, so the IP address of D. Okay. So in direct forwarding, the destination MAC address corresponds to the destination IP address. In indirect forwarding, the destination IP address is the final destination. The destination MAC address is the local destination, so the local interface of the router. Okay. What happens in the router? So the router has to decide where to send a packet that is received with a given destination. And the router is usually connected to several interfaces, so the forwarding decision is what is the interface to use, where to send the packet. And the packet is released to the next hop, okay? Is released to the next hop, which is the next router that is getting closer to the destination until the packet will arrive to the destination. The decision is taken always looking only to the network ID portion of the IP address. Okay, so the router receives a packet with a complete destination address, which is composed of 32 bits. This is very important to remind. The destination address is always 32 bits. But it only looks at what the router can understand to be the network ID portion of that IP address. Okay. This is because all the hosts attached to the same network are stored in the router forwarding table as a single entry. And this is a form of address aggregation, and it's really important because otherwise you will have routing tables of huge size. Okay? They are already of huge size, but if you write in the routing tables each single host, then they will explode. So in the routing table you find entries that are not actually hosts, destination hosts, but network destinations. For example, here this router, when it has to send the packets to any of the hosts that are attached to that network 131.175.0.0, we have an entry here. The entry is reports only the network address of that network, so the network prefix of that network, and then in the other column, what is the next stop to use. The next stop is usually the IP address of the interface of the router that should be used as next stop. So in this case, the router is this router here, and what you find is the IP address of this interface B. Okay. So each time this router receives a packet that is destined to one of the interfaces that I have marked in the left, they belong to that network, so the packet is sent towards B as next stop. And here you have the opposite. So each packet on that router on the left that is destined to any host or any interface belonging to the network 131.30.0.0 is sent towards the interface A of the intermediate router. Okay. So if we look more closely at a routing table, in the routing table you actually find the first column, which contains the destination addresses in terms of network prefixes. Then you have a column which contains the IP address of the next stop router, or better, the IP address of the interface of the next stop router to reach in order to hand over the packet. And you can also find the local identifier of the output interface. This is to, let's say, facilitate the forwarding operation. The column of the destination prefixes is actually containing entries, and each entry is not corresponding to a single IP address, but to a range of IP addresses. The range of the IP addresses is given by is identified by the network prefix and its length. Okay, so you have to always report in the table not only IP addresses as destination, but pairs of addresses and lengths. That may be, for example, addresses and associated net masks. It depends on the implementation. For example, the entry that is marked there, that is 167.24.103/24, refers to a network prefix of length 24, and this means that it refers to this range of IP addresses going from the .0 to the .255. Okay. So when you receive a packet, the packet has a destination IP address that is specific, and if the destination IP address falls into this range, then the packet is matching that specific item of the routing table. Actually, in a router, before searching the routing table, there is another operation that must be carried out in advance with a higher priority. And the first operation is matching the received packet and the IP address of the received packet with the addresses of all the interfaces of the router. This is to identify the cases where the packet has to be forwarded in direct forwarding. So if the destination of the packet is directly connected to the router, then you don't have to use the routing table. but you have to send the packet out of the interface where this destination is connected to. So the first operation is to take the IP address of the packet and match it against the IP addresses of the interfaces. How this is done? So when you configure the IP address of an interface, you have to specify an IP address and a net mask. Okay. This net mask specification refers to the interface, not to the received packet. Okay, is the local interface. The local interface is always configured with an IP address and a net mask. And this is because the local interface has an IP address that belongs to an IP net. Okay, so by specifying the IP address of the interface plus the net mask, you are also specifying the network prefix of the network that is connected to that interface. Okay, so the interface belongs to the network, and the address of the network is contained in these pairs of configuration parameters. So in order to match the received address with the interface address, you have to take the received address, do an AND operation with the net mask of the interface, and then do the same with the IP address of the interface. And if they match bit by bit, so the result is identical, then you have a positive match. Okay. So that means that the packet is directed to a host that is directly connected to that interface. So the packet must be sent out to the interface. Okay, so remind that the net mask is always associated to the interface, not the received packet. So this check must be done for all the interfaces of the routers, except the one that received the packet. Maybe. So all the interfaces of the routers have to be checked. If you don't find any positive match, then the router must start looking at the routing prefix, at the routing table, because this means that the packet must be forwarded in an indirect way. So it must be given to a next hop router. So then the router performs a lookup into the routing table, and again we have to match the routing table. We have to check matching of the received packet with the routing table entries, entry by entry, and we have to find all the possible matchings. In this case, when you are looking into the routing table, it may happen that the packet matches more than one entry. Okay. So, but the final decision must be univoc. So, how to solve this problem when you have matchings with more than one entry? The router applies the longest prefix matching rule. So it means that if you have matching with more than one entry of the routing table, the entry where the matching is longest is selected. So the entry where you have the net mask containing a higher number of ones that is matching with the packet. Okay. Now we will look at some examples in order to make it more clear. Why we need to apply this longest prefix matching? When you look up into the routing table, and we didn't talk about longest prefix matching when we were looking up in the output interfaces. This is because a packet can match at most one interface address. Never you will have a packet that is matching two interfaces in the same router. And this is because in a router you can never assign more than one interface to the same IP net. Okay. If you assign two interfaces to the same IPNet, this is a misconfiguration. Usually, if you have a router with a smart operating system, you will not be allowed to do it. Because if it would be possible, then you would have undefined routing decisions. Okay, so you don't have to apply longest prefix matching when you are looking at the interfaces, because the matching will be only one. Instead, inside the routing table, you can have more than one matching. Okay, this is very important to remind also when we will look at all the algorithm for IP address lookup. Another important trick that is very applied in almost all the routers is the default routing entry, default router entry. So in the routing table you have several destinations, but in almost all routing tables of almost all routers, you always have an entry which is 0.0.0 as address and 0.0.0.0 as net mask. Okay. What is the meaning of these two pairs of addresses and net mask? Since you have a net mask of length 0, by convention it means that this line will match with any IP address of all packets. Okay, so all the packets match always with this line. But since the net mask is of length 0, this is the shortest possible matching. Okay, so this line will be selected as the winner of the lookup operation only in the case when you don't have any matching in the other lines of the lookup table. And this means that the packet is not matching with any specific entry. So basically it's a packet going to a destination that is unknown to the router, and therefore the router has to do something about it. And the decision in the routing architecture of IP is that the router that has an unknown destination packet handle this packet to another router that is connected, which is the default router. So a router that is entitled to manage all the packets going to unknown destinations. All the routers are configured in this way in the edge of the network, except routers that are in the core of the network, because otherwise you will have undefined looping of packets. Because it may also happen that there is a packet with a destination that is really non-existing in the whole network, so in the whole internet. So in this case it must be dropped. So there are some routers in the core of internet, very large, which don't have any default router, typically routers in the tier 1 internet service providers. But all the other routers always have a default routing line. So let's consider an example in details. This is a router with a routing table and two interfaces already configured. The routing table has a certain number of entries specified in terms of network address and associated net mask. And here you have also the default router entry. And then you have on the third column the IP addresses of here they're called the first hop, but usually also called next hop routers. So where to send packets that are matching those entries. So this is on the left side. You have the packet that is has been received, and that is the destination address inside the header of the packet. So the first operation is to match this destination address with the interfaces, and in this case you have a positive matching with the first interface, okay? Because here you have the length of the network prefix is 24, and it is matching with the address of the packet when you do an end operation, bit-to-bit end operation with the net mask. Okay. So this packet is sent in direct mode, direct forwarding towards interface 1. And that is enough, so you don't use the lookup, the routing table for this packet. This is another packet that is received. Again, it is matched against the interfaces, but in this case you have no matching, so you have to look up into the routing table. And you can see that this packet does not match the first entry, because there you have net mask of length 24. If you do the end with that net mask and the destination IP address, you find 131.175.16, and the entry is .15, so they are not matching. You find matching with the second line, but you cannot stop here. You have to look at all the table to find all the possible matchings. Then you don't have matchings in the other lines. And finally, the last line is always matching with all the packets. Okay? But the length of the prefix that is matching in the first line is 24, which is larger than the prefix of the last line, which is has length 0. So the first line is selected, and the packet will be forwarded to the next hop router with IP address 131.175.21.2. Okay. Now this is another packet. This is not matching with any specific entry of the table. No, sorry, it's matching with that entry. With that entry and this entry. So this packet is matching with 3 entries. We have to select to apply the longest prefix matching algorithm. So in this case, this is the longest prefix matching line, so the packet will be forwarded there. And last, this is a packet that is not matching with any specific entry. It's only matching with the default routing entry, so it will go to the default router. Okay. You can display routing tables in the routers using the operating system of the routers. However, it's not very easy, because it's not very common that you can manage a router. But if you want, you can also display routing tables in your PC, because also the hosts have routing tables. Okay? They are used when you don't have a single route specified that is towards the gateway, the default gateway, but you can specify other routes. So if you have a Linux system, the routing table displays in that way. You can see that there are several additional columns compared to the simplified vision that we had for the the purpose of the examples. And you can display the same routing table also if you have a Linux system. There is the command root print that allows you to look at routing tables inside your system. So this is basically the part dedicated to the forwarding mechanism. Now just start in the next 5 minutes the second part of this overview, that is dedicated to IP addressing. So once we have understood this mechanism based on IP nets, now we have a look to the criteria used to assign addresses to the networks. Actually, this is not directly relevant when you are performing a single forwarding operation on a single packet, but it's good to have a global picture because, of course, just always have to ask the purpose of what we are studying. And moreover, by looking at the addressing mechanism, we can better understand why we have to use this longest prefix matching mechanism in order to route the packets. So at the beginning of IP, the addressing scheme was based on the so-called classful addressing system. I told you that when you are assigning a network address, the length of the network prefix is variable. Okay, so there is a variability of the number of bits in the IP address that are used to identify the network and the number of bits that are used to identify the host. So at the beginning of IP, this partition was fixed by a rigid set of rules, and networks were divided into three classes, A, B, and C. Networks belonging to each class had a different length of the prefixes, of the network prefix. And in particular, in class A, the network for all networks in class A, the network prefix is taking only the first byte, and so networks that are in class A are very large, and large because each network has a very high number of hosts. In fact, if you take the first byte for identifying the network prefix, you have 3 bytes, so 24 bits to identify the host. The number of addresses that you have, so the size of the block of addresses that you have for the host tells you how many hosts you can connect to that network. So in this case, you can assign 2 to the 24 addresses for the host, which is really a huge number. On the other side, the number of networks of that class that you can define is limited because the number of networks is given by the length of the network prefix. Okay. In this case, the network prefix is only 1 byte long. Actually, in the classful system, you cannot even use all the bits of the network prefix in order to identify networks, because the classful system is based on a code that is composed by the most significant bits of the IP address. That code identifies the class. Okay, so class A is identified by setting the first bit, the most significant bit of the first byte, to 0. Since the value of this bit is fixed, must be 0, the number of networks that you can define in class A is not 2 to the 8, but is 2 power 7, because you have 7 bits that are variable in your net ID. In decimal notation, this means that the IP addresses of class B starts with a byte that has a decimal value from 1 to 127. Okay. Actually, only to 1 to 126, because as we will see next time, the address 127 is reserved for special use. Okay. So the number of networks of class A are limited, but their size is very large. Then you have class B, identified by the code 10. So you have 16 bits for the net ID and 60 bits for the host ID, 2 to the 16 hosts addresses in each network, and the number of networks that you can find that you can define is 2 to the 14, okay? Because 10 it must be always the same. The decimal value of the first byte goes from 128 to 191. Okay. Class C, the code is 110. In this case, you have 4 bytes for the net ID and 1 byte for host ID. So in this case, you have very small networks. The number of addresses in each network is 256 actually. And the number of networks that you can create is very large. The first byte goes from 192 to 223. Okay. Then there were other 2 classes that were defined. One is reserved for multicast addresses with code 1110, and the last one was left for future usage. Okay. So in order to identify the class in the classful addressing system, the router looks at the values of the first bits. So if it is 0, the first bit is 0, it's class A. If the first 2 bits are 10, it's class B, and so on. We as human beings can understand the class from the decimal value of the first byte. So if you see the ranges, so if you have an address that in the decimal notation starts with a number that is between 192 and 223, let's say 200, then you know that that is an address belonging to class C. Okay, so on and so forth. So in this classful system, there are only 3 possible net masks. One is the 255.000, and then the other ones are you see them there. And each net mask is rigidly associated to the class. Okay, so actually, since the class is can be understood by looking at the first bit, a router does not need to have entries in the routing table which also report the length of the net or the IP, the network prefixes, because the length of the network prefix is automatically evaluated by looking at the first bits. This only holds is something that can be done only conditioned to the fact that all the addresses, the network addresses, are according to this classful system. As we will see, this is not true anymore. So nowadays you need to explicitly indicate also the net mask. So actually this classful system is not used anymore, but it's important because there is a set of addresses that have been defined and used for special purposes, which were defined at the time of the classful system. So they are basically following more or less that system. And they are listed here. So specifically, the network address with all zeros can be used when there is a source, so maybe, for example, a host, which does not know immediately it's the IP address of its interface. So in this case, it will send it can send packets to outside this interface, but it cannot write a specific IP address as a source IP address. Okay. So in this case, it will write all zeros. Then there is the IP address with all ones. That is called a direct broadcast address. Limited broadcast address with all ones in the net ID and also in the host ID. So in this case, the packet that is sent to the destination using this specific address is a broadcast packet. So it must be received by all the interfaces connected to the same network. It is, however, a local broadcast network. So the packets that have this address stays only inside an IP network. If the gateway, the router connected to this network, receives a packet with that destination address, it will drop the packet. It will not forward it to other routers. So this can be used as a destination. There is also the possibility of sending a packet to a specific destination network, asking for this network to broadcast the packet to all the hosts. And this is the direct broadcast address. Direct in the sense that it's directed, so it's directed to a specific network. So in this case, you write a net ID as address. There's a specific network address, and the host ID is all ones. So it means forward the packet to all the hosts. And it can be used as destination address. Actually, most of the networks does not support this function, because otherwise you can easily saturate networks with sending this kind of packets. Then there is the specific host in this network. This can be used for direct forwarding as destination. So when I'm sending a packet to a destination that is on my network, it's useless that I indicate any net ID, because the packet will be forwarded only to another host. So net ID is all zeros and the host is specific. Then we have the network address. That is another reserved address, because when you specify net ID and you set all the host ID to zeros, that is the network. It's not used in practice, but it's used to identify the network. And it is used in the routing tables. And finally, there is this one network of class A, that is the network number 127, which was used for the loopback purpose. So when you are sending a packet with the destination net ID 127, the packet is forwarded back by your local network interface to the system. So basically, the packet that is sent by the operating system outside reaches the network interface, but then goes back to the operating system. It's called a loopback, and you can use it, for example, to test the network with the network interface, or for other purposes as this specific target. Last, the private addresses. Okay. So we said that an IP address is associated to a single host. It cannot be repeated anywhere in the network. However, when classes were defined, it was decided to leave some address blocks to make an exception to this general rule. Okay, so you have addresses, the blocks of addresses in each of the three classes of the network, that are dedicated to private addresses. And there is one block in class A that is identified by the first byte at 10. Then there are 16 blocks in class B, going from 172.16 to 172.31, and 256 blocks in class C, from 192, starting with 192. These addresses can be reused, so assigned to several, to different hosts and interfaces. However, with the condition that the network that is where these hosts are connected is isolated compared to the rest of the internet. So it means that if you have a private network that you can manage as a private in a private way, you can use these private addresses. When the network is connected to the rest of internet by a router, the router that is connected to the rest of internet is not allowed to send any packet that has these addresses as destination or source IP address outside the private zone. Okay, the private kingdom is kept separated, and in order to send packets outside, you need a system that is called NAT, that is network address translation, in which by several techniques that we don't look specifically in this course, these addresses are translated into public addresses. Once addresses becomes public, then you can send the packet over the rest of the internet. And this was a system that allowed to increase the number of hosts despite the limitation of the address space. Okay, otherwise the address space is very limited. Okay, we stop here. So next time we will continue closing this part of overview, and then we will start to speak about algorithm to speak about the router architecture. Okay.